morning guys, this is paper 2-1, which means statistics. Number 1, a sixth form college has 84 students in year 12 and 56 students in year 13. The head teacher takes a stratified sample of 40 students, stratified by year. Part A. Describe how this sample could be taken. Okay, so what we need to know first of all is what fraction of the year groups are being taken. So we need to work out how many students there are in total. So 84 and 56 is 140. Now we're sampling 40 of those. So that is 2/7. So we want 2/7 of year 12 and 2/7 of year 13. So this means then he wants 2/7 of 84 is 24 year 12 and 16 year 13. Now, from there, assuming he wants a random sample, we would now say assign each student in each year group a number, set up a random number generator, generate numbers until he has all the students he needs. The head teacher is investigating the relationship between the amount of sleep S hours each student had the night before an aptitude test and their performance on the test P marks. For the 40 students, he finds the regression line for P on S to be P is 26.1 and 5.6 S. B. With reference to the equation, describe what effect an extra 0.5 hours sleep may have, on average, on a student's performance in the test. So, looking at the model, if someone had 0 hours sleep, then we would expect them to score 26.1. If they had 1 hour sleep, it would be 26.1 and 5.6. So every 1 hour gives them 5.6 more marks. So 0.5 times 5.6 is 2.8. So we would expect an extra half an hour sleep to result in 2.8 more marks. So you'd want to say something along the lines of they should score 2.8 more marks. Final part, describe a limitation of the model. So the most obvious one is that there is no cap on the amount of sleep a student can have. So technically P has no limit, which is rubbish because there's only going to be a set amount of marks on the paper. Number 2. The Venn diagram shows events A, B and C and their probabilities. B and C are mutually exclusive, so they can't happen at the same time, and A and C are independent. Find the values of x, y and z. Okay, x is easy because there is no overlap to B and C, so x is 0. Okay, so not so easy from here. So what else do we know? Well, we know that probability altogether has to add up to 1. So if we add all of the numbers together, we get 0.85. So we know 0.85 add y add z is equal to 1. So that tells us y add z is 0.15. Okay, so that's not much use on its own. Now, we also know that A and C are independent. Now that means their intersection is equal to the probability of A times the probability of B. So, we might then want to write the probability of A intersection C is equal to the probability of A times the probability of B. Okay, so we know then the intersection is Z. Now, the probability of A is 0.1 add y add z. And then the probability of B is z at 0.39. Okay, now inside the first bracket, we know that y add z is 0.15. So, we know that z is 0.25 times 0.39 add z. Or z add 0.39 Okay, so now we're going to expand on the right. So we get Z is 0.25Z at 0.0975. So 0.75Z is 0.0975 divided by 0.75 and we get Z is 0.13. Now we know y add Z is 0.15, so y is 0.02. Number 3. A fair five-sided spinner has sides numbered 1, 2, 3, 4 and 5. The spinner is spun once and the score is recorded. Part A. Write down the name of the distribution we can use to model the score. Okay, so we can count the outcomes 1, 2, 3, 4 and 5. See? And so that means it's discrete and the probabilities are the same or uniform. So it's called discrete uniform. Part B. The spinner is spun 28 times. The random variable x represents the number of times it lands on 2. Part 1. Find the probability it lands on 2 at least 7 times. Alright. So, the spinner either lands on 2 or does not. So, this is binomial. So we can say x is binomially distributed n is 28 and p is 1/5 or 0.2. Okay. So, we want probability x is greater than or equal to 7. Now, our calculators always calculate probability from the left and up. So, we need to think of this as 1 minus what we don't want. So, we are not interested in 6 or fewer. Okay, now on your calculator, you want to go into menu, distribution, and then you want binomial CD, and then you want variable, x is 6, n is 28, p is 0.2, press equals, and you will get 0.678. So that gives us the final answer of 0.322. And for part 2, we want the probability x is greater than or equal to 4, but less than 8. So, that means then we are interested in 7, 6, 5, and 4. So, we want the probability x is less than or equal to 7 minus 3, 2, 1, and 0. So the probability x is less than or equal to 3. Okay, so again, you want binomial CD, so we get 0.818 minus 0.160. That was my postman, sorry. And then that is finally going to give us 0.658. Number 4. Joshua is investigating the daily total rainfall for Herne from May to October 2015. Using information from the large dataset, he wants to calculate the mean total daily rainfall. Part A. Using your knowledge of the large dataset, explain why he needs to clean the data before calculating the mean. So, the large dataset is a very strange one. It's different every year. So, don't worry about this one too much. So, in the large dataset, which you can get from the Edexcel website if you really want to, some of the days for rainfall have trace instead of numbers. So, what you would need to do is ignore any days where there was a trace and then calculate the mean using all the others. Using the information from the large dataset, he produces this grouped frequency table. Very exciting. Part B. Use a linear interpolation to calculate an estimate for the upper quartile of the daily total rainfall. So, what we need to do, imagine we put all these days in order of their rainfall. We want to find the 75th percent day and its rainfall. So, the first thing we need are the total number of days. So, if we add up the frequency, we get 184. Now, we want the 75th percent day, so we want 3/4 of that. Now that is 138. So, we're now going to go through the frequencies in the table, add them up, try and work out where 138 would be. So, starting at the top then, we have 121. Add 10 is 131. And then add 24, and we get 155. So, the day that we care about is in that third interval. So, we know the upper quartile is 1 plus something. We'll work that out in a moment. So, the upper quartile is 1, add, now then, up to and including the second interval, we have 131 days. So, we need to go 7 days into the third interval. Now, there are 24 days in that, so we are going 7/24 into the interval. Now, the interval is 4 wide, because it's going from 1 to 5. So, we're going to have 1 add 7/24 times 4. And that gives us 2.17. And now because that's rainfall, it's millimeters. See, calculate the standard deviation. Okay, so for that, we are using these two, and we are given the formula. So, for us then, sigma x squared is sigma fx squared, and the mean is sigma x divided by the number of days, 184. So, for us, sigma is the square root of 7,704.1875 over 184. Minus the mean, minus the mean squared, so minus, now again, the mean is sigma fx divided by n, 184, so 539.75 divided by 184. And that is squared. Now, calculate that, and we should get 5.768. D part 1. State the assumption involved when using class midpoints to calculate an estimate for the mean from a grouped frequency table. So what we are assuming is that inside each interval the data is spread out evenly or uniformly. So it's not, say, in an interval that's 10 wide, we're assuming that instead of the data maybe all being towards the bottom or the top end of the interval, that it's uniformly spread throughout the whole interval. And then what we're doing is we use the midpoint as the average from that interval. Part 2. Using your knowledge of the large data set, explain why this assumption does not hold in this case. So again, you probably don't know anything about this large data set. Don't worry too much. So the reason is that most of the data in the first interval were actually 0. So data in the first interval certainly were not uniformly spread throughout the interval. Part 3. State, giving a reason whether you would expect the actual mean to be larger than, smaller than, or the same as the one we calculated from the table. So, as I said in part 2, most of the values, or a lot of the values, in the top interval were actually 0. Now, we've used the midpoint in the top interval as 0.25. So, we've overestimated those zeros. So we will have calculated a higher mean, so the actual mean will be smaller. Number 5, the last bit of horrible stats. Past records show that 15% of customers at a shop buy chocolate. Good times. The shopkeeper believes if he moves the chocolate closer to the till, then a higher proportion of customers will buy chocolate. After moving the chocolate closer to the till, a random sample of 30 customers is taken and 8 of them are found to have bought chocolate. Julie carries out a hypothesis test at 5% level of significance to test the shopkeeper's belief. So we're given a hypothesis test. Part A wants us to identify the first two errors Julie has made. So let's have a look. So a null hypothesis, H0, the proportion is equal to 0.15. That's fine. Our alternate hypothesis, H1, the proportion is greater than or equal to 0.15. And that is an error. So that should be that the proportion is only greater than 0.15. Okay, next, she's defined the variable, so that's good. Then she's set up the distribution, so that's all good. Now the next error is that she's found the probability x is equal to 8. That's an error. What will B explain whether or not her errors will affect her conclusion to the hypothesis test. So, she ended up getting a probability less than 5%, which led to rejecting H0. So, if we find the probability x is greater than or equal to 8, so that's 1 minus the probability x is less than or equal to 7, we get 1 minus 0.93, which is 0.07. Now that is bigger than 0.05%. So, we should not have rejected H0. So, the answer is yes. She has made the wrong conclusion. So, H0 should not have been rejected. C. Find, using a 5% level of significance, the critical region for a one-tailed test of the shopkeeper's belief. The probability in the tail should be less than 0.05. So, what this means is, find the smallest number of customers that had to buy chocolate out of the 30 to then reject H0. So, we know the probability that x was greater than or equal to 8 was 0.07. So, quite close. So, let's try the probability x is greater than or equal to 9. So, that's 1 minus the probability x is less than or equal to 8. So, that gives us 1 minus 0.972. And that is 0.028. So, that means under the null hypothesis, it's only 2.8% likely 9 or more of 30 would have bought chocolate. So if 9 or more had bought chocolate, then we would accept H1. So the critical region is x greater than or equal to 9. Okay then, part D wants the actual level of significance of this test. So, as I said, that's 2.8%, or if you've gone to more accurate decimal places, 2.78%, but for me, it's 2.8%. Okay then guys, that's it for the stats. Now I'm gonna do the mechanics. Hope to see you there. Really hope this has helped. Good luck in your exams. Take it easy. Take care.